Welcome to the nature of covalent bonding, our first section of this unit since section 1 was covered with chapter 7. Now let's look at the octet rule again. When atoms bond covalently, they do so to acquire a more stable electron configuration. Usually this means to acquire a full octet of valence electrons. Now, electron sharing, as we learned in section 1, is called covalent bonding and involves sharing pairs of electrons. When two atoms share one pair of electrons, we call it a single covalent bond. The reason we call it single is because the atoms are sharing a single pair of electrons. If we consider F2, which is forming in the diagram here on the right, we can see in the top that we have two fluorine atoms, each of which have 7 valence electrons. As they come closer together, those single electrons that are not paired up can form a pair together and be shared between those two nuclei of the fluorine atoms. Now, this shared pair of electrons is frequently represented with a single dash between the atoms, which indicates a single bond. So, as I just mentioned, structural formulas will most often use dashes to indicate bonding between atoms. Now, you need to remember that each dash represents 2 electrons, not just 1. Let's try to draw the structural formula for ammonia, which is NH3. We begin with drawing electron dot diagrams of the atoms involved. We have nitrogen and 3 hydrogens. We put the dots around nitrogen, and there are 5 there, and each hydrogen is going to have 1 valence electron. Now, as we try to connect these together, each hydrogen can only bond 1 time, so we wouldn't have them bonding to each other because then they couldn't join with the rest of the atoms. So nitrogen, having the most electrons available for bonding, is going to be more at the center with things coming off of it. So nitrogen goes in the center, and it has an unshared pair. It has 3 places for hydrogens to bond. And so the structural formula for ammonia would look like this. Now, there were other electrons around nitrogen. There's a pair of electrons that are not part of a bond, and those electrons are called an unshared pair of electrons. Sometimes they're also called lone pairs or non-bonding pairs. Some elements have several unshared pairs. The halogens, for example, always have 3 unshared pairs. Oxygen usually has 2, as you can see in both of these molecules. Let's consider the following elements. How many electrons would each of them need to share, or how many single bonds would each need to form in order to achieve the same electron configuration as neon? As we can see in this diagram, carbon has 4 single electrons, so it can bond 4 times. Nitrogen only has 3 electrons available for bonding, so it can bond 3 times. Oxygen can bond twice, fluorine can bond once. So let's try drawing the structural formulas for these compounds. With OF2, that means we have 1 oxygen and 2 fluorines. If we draw their dot structures, it would look like this. Now recall, halogens can only bond 1 time, so they wouldn't bond to each other. That would put oxygen in the center, and it would be able to bond once to each of the fluorines. SCl2 is also going to look similar to this first molecule because sulfur and chlorine have the same electron structures as oxygen and fluorine. So it's no surprise that it works out in the same way with sulfur at the center and the 2 chlorines coming off of it. Now N2H4 has a lot more atoms to deal with, but we still would work it in the same way. We draw both of the nitrogens and all 4 of the hydrogen dot structures. And as we look at this, we can see that each of these nitrogens can bond 3 times. So they're definitely going to be more towards the center of our molecule. We can bond them to each other once, which leaves each one with 2 single electrons ready for bonding that can be shared with these hydrogen atoms. And so our molecule would look like this. Now, I'd like for you to try drawing the structural formulas for these, and we will discuss them in class. Now, is that all that there is? Let's remember the diatomic elements, H2, N2, O2, etc. Those 7 elements that most of which form the shape of a 7 in the periodic table other than hydrogen. If we draw dot diagrams for 2 oxygen atoms, they would look like this, each having 6 valence electrons. How could these two atoms bond together and both attain their octet of electrons? It looks to me as though they're going to have to bond with each other more than once. If the atoms formed two bonds between them, then each would have an octet. When two atoms form multiple bonds between them, the bonds are referred to as double or even triple covalent bonds, rather than being thought of as multiple single covalent bonds. In the oxygen example, the structure appears to work out if the oxygens double bond, as you see here. Now, in reality, not everything is going to work out as we would predict. Your textbook points out that oxygen appears that it should work out this way, but that experimentally it's been found that two of the electrons in the oxygen molecule remain unpaired instead of bonding. So, although these rules provide guidelines to help you figure out molecular bonding, this example demonstrates that sometimes things don't turn out as expected. They break the rules, and you should understand that. Now, that doesn't mean that it's something that you're going to easily be able to predict. You would need to have the experimental evidence there that would lead you to that conclusion. So the examples that I give you, for the most part, are not going to break the rules. There will be a few, but the ones that I give you that do break the rules, it's going to be obvious. Whereas here with oxygen, it was not obvious that it was going to break the rules because it looked like it worked out so nicely with that double bond. Now let's try predicting nitrogen's structure. Now, it doesn't break the rules. If we draw dot diagrams for two nitrogen atoms, we see that each one has 5 valence electrons, which means each one's available to bond 3 times. How could these two atoms bond together and both attain their octet? The only way it would work out is if those two nitrogen atoms were to triple bond to one another. Let's try a molecule that's composed of more than 2 atoms. Let's predict the structure of a molecule of carbon dioxide. Now, CO2 has a carbon and 2 oxygens. Their Lewis dot diagrams would look like this. And we can see that carbon can bond up to 4 times, but each oxygen can only bond twice. So that would make it look like carbon's going to do most of the bonding, so it's likely that it should be put in the center. So we'd start out looking like this, and we would be able to form 2 bonds between the carbon and oxygen on the left and 2 more on the right, giving a diagram that looks like this. Now, what type of bonds are those? Are those 2 sets of single covalent, or is there another name for them? Hopefully you recall that these are each called a double bond, so we'd say carbon double bonds to each of those oxygen atoms. Now, I would like you to try hydrogen cyanide, so pause this video and try it. Hopefully you came up with your Lewis dot diagrams, and looking at this, carbon can bond the most, so you'd put it in the center. And then carbon can bond only once to hydrogen because hydrogen can only form 1 bond, which would leave it with 3 bonds going towards nitrogen. And what type of bonds are these? The one on the left, going from carbon to hydrogen, would be a single covalent bond, but the one on the right, recall, is called a triple covalent bond. Last of all, I would like for you to try formaldehyde, keeping in mind this general rule about thinking of a central atom. These are going to be your atoms that can form the most bonds. Terminal atoms just refer to those that can only bond once, so of course they're not going to be in the center. And try this on your own, and we will talk about it in class. See how you did. Now, let's consider the valence electrons of the elements in the second period. If we look at lithium through neon, this is what their dot structures look like. And let's use those dot structures to predict how many bonds each atom must form to attain a noble gas configuration. Okay, with lithium, it only has 1 electron. It can only bond 1 time the way that it is. Beryllium has 2, so once again, it can only bond 2 times. And boron has 3, it can only bond 3 times. So do those really form a noble gas configuration? We'll talk a little more about that on the next slide. Carbon, we've already seen, can bond 4 times, and that will get it its octet. Nitrogen, don't be fooled, it's got 5 valence electrons. The pattern does not continue upward. It's going to count downward now because we have some unshared pairs that are not usually involved in bonding. And so nitrogen is going to only form 3, oxygen only forms 2, and fluorine can only form 1. Can lithium form a covalent bond, though, and reach stability? If it's sharing electrons, as it would in a covalent bond, then it would only have 2 valence electrons to count for itself, and it's in the second energy level. Therefore, it's not filling its outer level with just 2. Only the first energy level, hydrogen and helium, can fill up with just 2. So it's not going to reach stability using a covalent bond. It's going to have to use something else. If you recall, lithium is a metal, and so if it bonds with a nonmetal, instead of forming a covalent bond, it might transfer that electron. It's still a bond, it's still depicted in a diagram with a dash, but that electron is essentially pulled away from the lithium, and therefore it empties out its outer shell. So it reaches stability through ionic bonding, not through covalent. Now, which elements can reach stability, meaning an octet, by forming covalent bonds? And those are going to be the ones that can get a total of 8 electrons through bonding. And so as you look up there, recall, carbon was able to form 4 bonds, which would make it share 4 pairs of electrons, which would give it 8. So carbon, nitrogen, oxygen, and fluorine would all be ones that can reach stability through covalent bonding. Can fluorine form an ionic bond? If fluorine were to bond to that lithium, it definitely could bond with an ionic bond. But it can also bond to itself, which would not be ionic. It would be purely covalent because there's no electronegativity difference between 2 fluorine atoms. So it can bond either ionically with a metal or covalently with a nonmetal or metalloid. Are the bonds in nitrogen molecules ionic or covalent? That's a similar situation to the fluorine molecule. With a nitrogen molecule, 2 nitrogen atoms have no electronegativity difference between them, and so it's definitely a covalent bond that exists between them. Now, Earth's atmosphere is almost 80% nitrogen, but only about 20% oxygen. So this begs the question, why are there relatively few nitrogen-containing compounds as compared to oxygen-containing compounds in our world? The triple bond in nitrogen molecules is harder to break than a double bond, and it's considerably harder to break than a single bond. And recall, oxygen, although its diagram suggests it would double bond, experimentally it has been shown to only single bond and have those unpaired electrons available on each of the oxygens, making it highly reactive. Now, in order for plants and animals to get access to nitrogen, then the element needs to be converted to a compound, and that's called nitrogen fixing. It will occur naturally if lightning provides sufficient energy for atmospheric nitrogen to react with oxygen, forming different types of nitrogen oxides. These dissolve in rain and fall to the ground where they can be used by plants. There are also some nitrogen-fixing bacteria found in soil that are able to convert atmospheric nitrogen into usable compounds, but it's not something that's easy to do on its own. So it takes high-energy environments like the lightning exposure or a biological environment where those bacteria contain enzymes and such that give it the ability to do nitrogen fixation. Now, are those all of the bonds that we need to learn? If you try drawing carbon monoxide, the result makes it appear that carbon will break the octet rule. As we look here, carbon has 4 valence electrons, oxygen has 6. So when oxygen forms its 2 bonds, it leaves those 2 electrons that were drawn as unpaired as maybe pairing up. But when we count around each of these atoms, oxygen has its octet, but carbon is short. It only has 6. However, if oxygen were to slide over an unshared pair, such as that pair circled there in blue, and make it a bonding pair so that oxygen contributes both of the electrons in the bond, then both molecules would achieve an octet of electrons. What we find is that carbon and oxygen bond with a triple bond in this way. Notice in this diagram that both carbon and oxygen end up with an octet of electrons. They just do so in an unusual manner. This is where we'll stop, and the second part of this video presentation we'll pick up in our next video.